I'm actually speaking to start it off today, and we're going to talk about localized loads on FRP influences and remedies. So we'll go ahead and get started here. What kind of the general feedback that we've gotten over the years, and this is our sixth one, is that whether it's design engineers want a little bit more about analytics and calculations, but generally everybody likes case histories. They want to see real life problems. So I've got two presentations today that will kind of shine some light on that. I think Daryl has got another one later on that will be that way, and I think Tom, being an inspection guy, he's all about being in the plant. So I'm sure his will. So you'll see a lot of case histories, a lot of like hands-on kind of examples um, of kind of what to do and what not to do. And so hopefully that'll stir up some good questions here. Quick introduction. So basically we're going to talk today about some of the differences between FRP and steel, how they work together, what you need to think about when you have those kind of interfaces. We're going to talk about potential causes for local stresses, a little bit about loads on flanges. We're talking about external loads on tanks. Well, we're going to talk about pressurization events, and then we're going to talk about some preventive measures on maybe try to how to stay out of trouble with some of this. Simple definition for localized loads. So we're talking about elevated loads that are created by one or more influences. So we're not talking about just one thing. Usually when we see failures, it's a combination of influences that come together, and it just kind of pushes over the edge. We find FRP to be pretty forgiving for the most part. It's got a lot of flexibility, fairly strong. I mean, you think about steel, you don't think that way, but it actually takes a beating, and will do pretty well if you do 4 out of 5 things right. If you have just one thing that's a little bit short, usually it still does pretty good. And then obviously being localized, they're restricted to a limited area, and they can also be created by sustained loads or by intermittent loads. So just a little bit of kind of, so we have internal influences. Most of y'all will kind of relate to these. So we're talking about, internal pressure. We're talking about, thermal temperature, weights. So you got pipe weights, you got valve weights, valve hanging off nozzles, those sort of things. If we were talking about, say, scrubbers, for example, then we're talking about internal loads, being that platform inside the scrubber, baffles, those sort of things. Pressure surges and vacuum are examples of that. When we get to external, here's where we're talking about pipe loads. This is where basically we've got a tank or a vessel, and we've got basically a pipe that is expanding, contracting, maybe it's dead weight hanging off of a nozzle, but it's putting some kind of bending moment on nozzles, for example. Man loads, you've got somebody walking up on top of a tank head, those sort of things. Occasional loads, winds of seismic, obviously. Something gets overlooked quite a bit is settlement. In Florida, we see settlement. I'm from Louisiana originally. A lot of settlement can happen in Louisiana. If you look internationally, you go to Saudi or someplace like that, that's probably their biggest issue almost, it seems. So when we talk about external stress, this is, I found this, I don't remember, I've had it for quite a few years, but that can create a lot of stress if you show up to the job site and you find a 14-foot gator in your pipe. So I'd almost think this might be South Louisiana, but I really don't recall it anymore. But I thought it was kind of a cool picture. So one thing we want to start on, I mentioned kind of talking about, we see a lot of issues at like steel to FRP interfaces. So I thought it would be good to talk about properties to give you a framework of why things are the way they are. So this is a slide some of y'all may have seen before, but we like to show the properties just to get people to kind of remind them of where we're at. So here's carbon steel here, all right. So this is basically a coefficient of thermal expansion. Just for relative terms, we'll just call that the 6. You got stainless over here, and then here's FRP. This is hand layup versus like filament wound FRP at 18, and we're talking about at 180 degrees. And why we tell you the temperatures is because all materials will expand more as temperatures go up. If you go into the ASCB code books, in the back of the codes there are appendices for all the materials for piping, and you'll see that even steel, there's a different thermal coefficient between 300 degrees F and 600, 900, I think it goes up to 1200 degrees, something like that. But basically it increases for carbon steel even. So it's not a unique phenomenon. It happens for almost all materials. So, you know, if we're talking ambient, it's going to be a little bit more modest. That number is going to be maybe 12 to 15, something like that, depending on the material. And say process temperatures, it's going to be something more like this. And then you have like CPVC here, HDPE here, and obviously there more resin content there. That's what drives thermal expansion. The plastic is what is expanding, and FRP is the glass that actually restrains that expansion. So the higher glass content, excuse me, with in FRP, we find that we have less expansion. It's even like fiber direction. So if I have a tank that's say 70-degree wound, it's not going to expand near as much in the hoop direction as it does the axial direction, because in the axial direction it's got a low angle, so there's a lot of resin in that direction. So here's modulus of elasticity. So here's where we know carbon steel is. 29 million, 30 million is pretty common. FRP, this is hand layup, 1.5. You see where HDPE is. So it's quite dramatic difference here. But the thing about it to really take away from this is that carbon steel is a rigid material. You know, you see a pipe, you see a tank, there's not any flexure. You lay it on the ground, it always stays round. FRP, if it's big enough, it's going to flex. If you have a 24-inch pipe or duct and you sit it on the ground, it will deflect just under its own weight. If you measure it vertically versus horizontally, you'll see the horizontals all of a sudden longer than the vertical, because it's just flexing just under its own weight. So from our standpoint, we try to use that flexibility to our advantage. We want to take advantage of that. It keeps the loads down, but we got to keep it within limits. That's kind of the goal there. So it's not always a negative, but there is quite a bit of difference. So this is something I haven't put out, but I thought that we talk about it a lot, but this really tells a story. A lot of people, especially if you're have an engineering background, so this is our typical stress strain curve for carbon steel. So we have our basically elastic range here. We go through a yield point, and then it's going to basically start to deform more until it finally fails. This is what we know carbon steel to do. Usually that plastic deformation, where we have like thinning and stretching, usually about 20% or something in that order for carbon steel. So this is where FRP is. So FRP is going to go to the yield point. This looks exactly the same, and it's going to start yielding, and it's going to fracture very quickly, because basically you're ripping those fibers apart at that point. You're breaking the bonds between the resin and the fibers, and so we see basically what we would call a basically non-ductile behavior. So this is going to act, you know, that same failure point is very close to like cast iron, for example, if we're looking at metals. So really this is what we would call a brittle failure mode. So when we're designing it, so say this rise over run, this is the area where steel might be, where you have your allowable coming back from like yield is, you know, your yield strength in steel is pretty typical. Usually it's something around the 2, 2.5, 2.3, something like that is a very common kind of, if you want to say, a design factor for carbon steel. Well, FRP, we're down here. Okay, we're in the like the design factor of like 6 to 10. So if it's tanks, design factor of 10. So we're nowhere near this. So that's why that we're not worried about that too much. So because we know we're down here, because we don't want to get anywhere near there, and there's lots of influences that we can't always control. So even if we have some unknowns to deal with, some uncertainty, we know we're still going to be in a sweet spot. We're not going to worry. That's kind of the concept of the design approach behind FRP. So we're going to kind of get into some examples now. So here's a line carbon steel line attached into an FRP pipe. This is actually a good example because you see, I mean, I don't know, maybe this is 10-inch pipe, something like that, and then maybe next down to 6 there, but support there, support there, support there, probably right another support right underneath that valve. So I mean, in 20 feet of pipe, you see 4 supports. Okay, because there is probably 800,000 to 900,000 pounds hanging off of that. So you don't want that much load hanging off your FRP. So this is actually, it's probably maybe a little bit overdone. I think you could probably do it with probably 2 supports here and take out that middle one even, or take out that one altogether if you wanted to do that. But basically the attention has been put here that they understand that there's a difference in the loads produced, and you just can't hang that big load with valves and everything else off of FRP. Here's an example. This is a big heat exchanger, and we've got basically, this is a cooling water system inside a power plant. So what we learned here is we've got this 24-inch line that's tying into the top of this, and this heat exchanger, I think, was something around 50 or 60 foot long. And under normal operating condition, the power plant, it's usually running something around 160 to 180 degrees Fahrenheit. It's taking basically the hot water off and trying to bring it back down, coming back out. But we found that this heat exchanger was actually expanding and contracting as well. Carbon steel, every material expands, and it was moving something over, I want to say about 3/4 of an inch is what we found. So when we're analyzing that system, that's an input that we have to put for that interface. We just can't just call that rigid and say it's not going to move, because that whole vessel is moving. So this was a project that we were actually brought in after the fact. I like this example because it's very dramatic, and you'll get to that. But so this is basically a water treatment system where they're taking basically brackish water off the Gulf, and they're treating it, making fresh water. So you have basically you have all these pumps here pulling into a main header. You've got these things filter units over here, and then it's taking it off. But you can see here there's 1, 2, 3, 4, 5, 6 branches there, and there's an example of a typical support. So you got little steel T-frame there, and something that looks like a strap over the top that's probably not much more than like boxing strapping or something like that for shipping. It's very weak, but a lot of short nozzles. And what I'm going to show you is basically, for even though this is pretty low temperature, thermal expansion is an issue, and you got all these hard points, and there's just no point of flexibility. So this was hydro. Okay, it wasn't even operating. So this is hydro. So you can see that band there, that's the support. So we don't recommend this kind of support, by the way. Really narrow, they're sitting 20, I think this was around 24-inch pipe right on basically steel. Really, we want to see a clamp there, but basically I think they didn't vent it in this case, and it shifted, or they got a little water hammer kind of going on when they pressured it up, and it basically just snapped the T. Really, if we would have had a choice in there, we were saying that we would like them to push that back so we could get an expansion joint in there, because there's no flexibility in that line really. And either you have to like take it and put an anchor on either end so it doesn't expand and contract as well, and basically control the growth, or at that point you got to decouple it so that you don't have these kind of issues and aren't overstressing those nozzles. But these hard points, especially like when you're, the pipe is not going to move the pump, right? So you have to basically keep those kind of transitions in mind. So here's another one that we found in a chemical plant. You've got a line coming in here. This is like a scrubber system. So it's basically bringing in gas. It's going down through some filtration and coming out the bottom. That goes to the next one. So you see it here. The supports here aren't fabulous to start with because you see again the FRP. Maybe I don't think that's like a shield. I'm not exactly sure. It looks almost like tape, but but you have that basically sitting on steel. When you have something of this size, we find that because we do design supports that something in the order of between 12-inch diameter, 10-inch diameter, we see pipes start to deflect more under their own weight, and we start to see more pipe loads where it doesn't act like a rigid pipe anymore. So we start to see those localized stresses where at that contact point, we've actually seen pipes have like axial cracks right at that contact point. So when we get to pipes this size, we really want to see a full clamp to basically protect the pipe, keep it round, things like that. But really what I want to show you here is like looking at this. So you've got this cantilever here, then you've got this kind of double step here attaching to the nozzle here. It's a big nozzle. Like I said, I think this is around 24-inch or so. But basically, the way this support is, and there's nothing in between, basically all this weight here, to a great extent, at least 50% of it is hanging off that nozzle. We would really rather not see that. And in our inspection, what we found is this is actually the back side of that nozzle. Here's your tank here, probably looking from this side, probably looking from that stairway or catwalk over there. This is cracked all along the back side here. Now it's pretty robust flange. You can't tell you that that's under designed, but still you've got all this load hanging off the end of it. Really, that needs to kind of come into play when when we're doing pipe stress analysis. These nozzles, when we're looking at that pipe, they're not rigid. They're not close to rigid. If you actually did a like you have like a PV lead, I think, or something like that, where you're calculating nozzle loads. If you assume that was steel, rigid is like 10 to the 12 or something stiffness. This is going to come back at like maybe 10 to the 5, 10 to the 6, something like that. With an FRP tank, I mean, like I showed you before, they're very flexible. So they're going to flex. They're not going to carry that weight the same way. The stiffness is probably more like maybe a couple 100,000 versus a million or something more. So you need to think about what's the stiffness of nozzles when you're doing pipe stress against those. So here's another example. So you've got a pretty small vessel here. Maybe this is a maybe 8 or 10-inch pipe coming up. Well, so you got this long span coming in. It's probably supported way back behind here. So all that's in offsets. Sometimes you can get away with it where if you're coming straight in and dropping right in, you're kind of minimizing moments. But when you start putting offsets, it's just like a doubler. So you've got like twice the moments going in there, and then well, that didn't challenge enough, so we decided we'd just strap on a whole nother pipe and add these other fancy pipe supports here. Let's complicate it even more. So fortunately this is gusseted, so maybe it handles it all right. But I suspect it probably wouldn't meet any kind of design criteria. Well, we put it, it's not compliant probably. So you're definitely living in a gray area. Here's an example that I was kind of pointing to before, where we got a bottom nozzle, probably something coming off the bottom of a tank, and you got this big cast iron housing, and you can even see this is, maybe this is line pipe, or maybe it's just steel pipe coming off this. So you got all that basically hanging off of an FRP nozzle, and if you look at this, it's majorly cracked there. I had some other pictures that are even more dramatic. I mean, it just looks like it's shattered. But I think you kind of get the point here that when we have these, really, we would like to see that flange grabbed with like a flange support coming down and carrying that weight and kind of isolating everything else coming off of that as well. So external loads on tall towers, scrubbers are pretty typical for this. In this case over here, this is a storage tank. I don't remember exactly, probably 36 foot tall or something like that. This is where that construction comes in, is that you have hand layup. There's one thermal expansion coefficient. If it's like 55-degree wound pipe, it's a different one. 55-degree wound pipe is going to be a little bit less than hand layup. Like I mentioned earlier, oh, let me go back here. Oh, I'm going the wrong way. So typically we'll see a tank wound in the order of 65-degree wind, 70-degree wind is not uncommon. So you have one thermal expansion, and then this will probably be a little more like just a film wound pipe, maybe hand layup. So this is actually going to be a whole different one. So what happens is this is growing at one rate, this is growing at another rate, and you're going to see moments up here, and we've actually seen cracks in those nozzles as well. So just because it's all FRP doesn't mean it's all going to behave the same either. And here you've got kind of the same thing where you've got a filament wound pipe, you've got FRP pipes here. Not sure these could be centrifugally cast pipe. I'm kind of thinking that might be just by the look of the pipe. So that's got a whole different coefficient as well running up. And basically, but here you've got all this pipe here, and there's no anchor points here. You've got kind of guide supports. Those are probably U-bolts right there. So basically, that whole length of pipe is all resting down here. So if this is growing at a different rate, basically it's pulling on that nozzle where that nozzle can break as well. And this is likely, you got an overflow here, so this is likely a fill line here. You don't want to overstress those nozzles. So tank pressurization, overpressurization. So here's one that basically had a pressure spike where they had kind of a burp in the system, and they had a atmospheric tank or something close to atmospheric that saw, I think, more than 5 or 6 psi. And this is the top. It actually blew the top right off of the tank. This is kind of what it looked like. It's not pretty. We've seen a few of these now, and it's pretty dramatic. And you definitely start having a lot of discussions about, okay, this is an operational issue. It's not a product issue. It wasn't that it was a bad tank. It's an operational issue. This is what the bottom looked like. So the bottom actually ripped as well. So it basically turned it into a pressure vessel. So you got all this load pushing at the top, and it's pushing at the bottom the same way, but we got the anchor lugs at the bottom holding it down. So, well, it turns into a projectile, and that shell just lifted right off and just ripped at the bottom as well. This is a vessel here that saw a vacuum event. These are like through wall cracks here. What we see like up here where you have these hard points, where you have these thicker points where this might be a lifting lug or something like that. So that's like a block on the shell, and it wants to keep that round, but the shell wants to do something different. Starts to want to peel that away. This is a look at the manway on, it'd be probably the other side of the manway there, where this was flexing so much, basically that big thick laminate just got peeled off the wall there. So vacuum is a very big deal. Tanks are generally designed to be optimized for internal pressure, and storage tanks mild internal pressure. When we see vacuum, whether they're cylindrical tanks, whether they're flat, square tanks, rectangular tanks, that's even kind of a tougher situation. So pipe supports create localized loads. I hunted. We've got thousands of photos, and you go through it looking, you see stuff, look for one thing, and you go back and you can't find it. But FRP sitting on steel just is not a good thing. And to put it right at a joint, you're putting a joint at a high stress point as well. Really, you just don't want to see that. That's not even ideal in steel. But again, the bigger diameters, we want to see like real supports. We don't want to really see that sitting on directly on steel. If it was a smaller pipe, we'd at least want to see a rubber lined shield there that was banded in to kind of protect the pipe there. Because we've actually seen these pipes, like I said, crack at the bottom here. You also get abrasion where pipes expand and contract and actually will wear through the bottom. We've seen that a few times as well. So this is definitely a don't do kind of thing. Here's a good pipe. The pipe, obviously, it's been around for a while. Probably needs to be replaced. Pretty sure this is fiber cascades way. You can see all the fibers there. It's a pretty clear example. But the big thing here is that you've got a U-bolt here, and again, sitting on steel, really, we should have that um, protected with the shield. U-bolts are fine if we do those sort of things, but we really want to see those shields in there because it makes point loads on the pipe. You got the chance to have abrasion. So, shields are like the cheapest support you can get, really easy to make, and not hard to install either. Here's another example for support. So here's a couple stacks coming off of blowers here. You can kind of see it come up here, pipe sitting on the steel here, and then they're going up. This is the top end of that. And so you've got kind of some guide points here. Again, guide points, there's no kind of anchors to carry the dead weight. So all the weight of that riser, which was probably something in the order of 50 foot tall, is all resting on these points right here. Really not suited for that. This is probably closer to ductwork than like pressure pipe. So it's thin wall to start with. So, sooner or later, we may find that they see some problems there and really needs to be addressed with proper supports. So this was one of Daryl's projects. He had fun with this. So this was, they call this like the fish return, fish ladder. So in a power plant, basically, because they're pulling in seawater for cooling water, so they're pulling in basically lots of other fishing critters and things like that. But because everybody's environmentally friendly, we got to return them so they're back to their happy place. So they got to cycle the fish back to basically to the bay. So it's kind of cool to see it used like that. But this pipe saw a vacuum event, and what they were doing was basically they pigged it, and they didn't think about vent. So when they pigged it, basically they pushed all the fluid down and created a vacuum on the backside of the pig, and it sucked in the sides of the pipe. So I mean, so that's what you see right here. And this is the inside of the pipe, just to make no mistake, it went all the way through. This was something actually pretty local to us here that we went out to. So that operation needs to be thought of, and how are we going to operate it? We talked about select the materials before, and yes, we're going to operate it with acid, but are we going to do a decontamination with bleach or caustic or something else? Well, those are very harsh and very different pHs when you're doing those things. So you need to think about how you're going to operate it, what processes are going to have to go through, and that needs to be part of the design process as well. So this is actually the backside of that one I showed you earlier with all the pumps, and so these are on these 8-foot support poles here. So again, like I said, this is probably 16 to 24 inches here. All these hard nozzles here, and one of the things that I learned pretty early was that when you have piping loads on tall structures, and I remember I was doing work on a design for a power plant, designing structures for supports, and I had a W8 by 31, which is a super beefy beam that, I mean, is just super robust. It was about 8 foot tall, I want to say, and had a couple thousand pounds of load on it, and it was deflecting like 1.5 inches. Well, it's not an anchor point at that point when the whole structure is flexing like that, and these are more like 4-inch pipes going up 8-10 feet, something like that. I mean, they're just kind of holding it up there. There's no guidance or anything here. So not to mention, I mean, the supports are all wrong and there's no anchor points. But stiffness in structures matters as well, because you do have all those pressure loads, thermal loads, all of that as well. So this is kind of some of the result of that they saw here, and you can expect if thermal load, we're going to see if there's a failure. More times than not, it's going to be at a joint. I mean, the pipe's well made. It's the most controlled part of the manufacturing process. Then generally the fittings are a little bit more robust than the pipe, because they have to be thicker, and there are pressure indices there that require that. So the weak point is the joints, and that's again where the human contact is. Um, so, um, so this is very typical and not surprising at all. So to kind of start to kind of bring this to end, so how do we prevent these? And one of the things is that with everything that we do, we have stresses. So the key first part for FRP is understand the materials. FRP, if it's hand layup, it's going to behave one way. If it's filament wound, it's going to be a little bit different. Like we talked a lot about some of the plastics yesterday. They all have their behavior, and they're all a little bit different. You just need to understand what they do well and where the limitations are, and that's kind of the starting point. When it comes to piping, if we have any kind of process temperature, if we're looking at, say, I'd say when you get above 150 degrees, 140 degrees Fahrenheit, if it's FRP, you've got combined loads, you got pressure and other stuff going on too. You need to be looking at analyzing the systems. Understand if you're doing a brand new plant somewhere and you've got 500 lines to do, that you've got to make some choices and try to prioritize. And that's a challenge for the engineers, in the room for sure, because if we look at it, we're like, yep, every one of those needs to be analyzed because there's risk there and we can't tolerate that. But you have to find a way to focus on the highest risk and prioritize down from there and try to manage that. And hopefully you got some parallel lines where you can kind of take from one and use those best practices that you see from those ones that you have, and kind of mitigate that to try to find best performance. But stress analysis, we've got companies that plants that they have lines fail after 10, 20 years sometimes, and they're like, we know these were never analyzed. They send them up to us first now, get them reanalyzed, new supports, and then they'll put their new pipe in, replacing kind, because they know it wasn't right to start with, or they know that the right approach wasn't taken to that part of the project, because maybe they didn't know as much as we do today. That's part of it as well. Steel, when we talk about steel valves, piping, any kind of inline components, flow meters, things like that. Generally, we want to see those independently supported. We don't want to see steel hanging off FRP, not really a good approach. And then, to kind of go on a little bit more, we talked about, consider, differential thermal expansion. Look at all of the design conditions, water hammer, settlement, can vacuum happen, those sort of things. The keys are control your process. We talked about operating issues. So as much as you control your process, sometimes expansion joints are required. Sometimes there's just not enough flexibility in the system. We don't like to put expansion joints as a rule. We put them where we need them only. Again, FRP to steel is a challenge. And think about those stiffnesses, because what the programs want to tell you is not necessarily the rules. So we talked about supports quite a bit. Purpose of supports is protect the pipe. We want the clamps lined, so we talked about like rubber lining, clamps. I see one of these at least once a year somewhere. You go in where it was just put in just as a shim to hold the pipe position, but it never got it never got replaced. So bad supports can make a really good pipe look bad. I think I've kind of hit most of these now. So again, the biggest point that I want you to take away from this is we have loads everywhere, we have stresses everywhere, and the real key is identifying them, understanding kind of where they're coming from and what's there, and then you can work to basically to make sure that you're not always going to get rid of them, but you can just keep them within safe limits. That's what we want to do. we wanted to stay in the box. We define our kind of our safety factor and our working area, and we just want to stay in the box. We don't care if we're in the middle or if we're on the edge, but if we're in the box, we're good. So that's what we want to kind of focus on. So, and that's really all I have.